Okay, thank you very much. So I will speak on random maximal isotropic subspaces and Selmer groups. So first, I'd like to thank all the organizers for inviting me and also for arranging things so that to avoid any conflict yesterday, especially Carl Palmer's I'd like to thank. All right, and so let me, we've talked about Selmer groups already a little bit in this workshop, but let me just remind you of the definition using cohomology. So I'll start with an elliptic curve over a number field, E over K. And if you take the short exact sequence that defines the p torsion of the elliptic curve, you know, the exact sequence that has a multiplication by p map from E to itself in it, then if you take the long exact sequence of cohomology associated to that, then you get this top row here. And if you do the same thing over each completion of K, and you take the product, then you get this bottom row here, and you have natural vertical maps going down. Now, the whole point of writing this sequence down is to figure out what the Mordell-Weil group is, and in particular to bound this group. And it's hard to figure out what that is directly, so instead try to find its image in here. But then it's hard to figure out which elements here come from here. So instead we try to figure out which elements here map under beta that are locally in the image of the Mordell-Weil group. In the sense that they come, when you map them by beta, it's in the image of alpha. So that's obviously a necessary condition for it to come from the Mordell-Weil group. And so those elements of that top middle H1, that's the definition of the p-Selmer group. So it's not the ones that are locally trivial, but there's the ones that are locally in the image. Okay, and you can also define the Tate-Shafarevich group, which is, well, it's the kernel of the right vertical map, this one here, except without the p torsion. If you take p torsion there, then the kernel of that vertical map will be the p torsion in the Tate-Shafarevich group. And then from this diagram, you can extract this exact sequence at the bottom, which. And the whole point of this is that the middle term is, well, first of all, it's finite, and also it's computable, at least in principle. So that gives you a way of bounding the Mordell-Weil group. And then the hard part is, well, okay, there's the problem of separating out which part comes from the Mordell-Weil group and which part comes from the Shah. But okay, yes.
Can you point towards the screen instead of the? You got the laser pointer there.
I've got I think it's a very, what? Oh, there's a big, so you're talking about this? Yeah, maybe that's better. Okay. Yeah, so this thing here is finite and computable. All right. Oh, sorry about that. All right. All right, and the question is, how does the Selmer group vary in a family of elliptic curves? So Manjul Bhargava and Carl Rubin already talked about this somewhat. So I would just remind you some of the things that are known. So first of all, there's Heath Brown's result. If you subtract off, okay. If you subtract off the part that comes from the torsion, so we're sort of the uninteresting part, and you look at what's left, then he proved that it satisfies a certain distribution as E varies over quadratic twists of this elliptic curve. And then this was, so there's some funny distribution where this is, well, I mean, there's this normalizing constant here, and then this is the part that depends on D. Okay, and then this was generalized by Swinish and Dyer and Daniel Kane, and they proved the analog for twists of other elliptic curves, so satisfying some conditions. And then there's the work that Carl Rubin described due to him and Barry Mazur and Zev Klagsbrunn. So where okay, I'm not going to say it again. He already explained. Okay. And so these are about the distribution of Selmer ranks, and you can also ask about the average value. as Mundrel explained. So, and there are a few other results that came earlier, but that weren't as strong as what Mundrel proved. So first of all, in 2000, Gang Yu proved that if you take, instead of averaging over all elliptic curves over Q, if you average only over the ones that have rational two torsion, then he proved that there's an upper bound on the average size of the Selmer group. And this means, this bar on the average just means it's average in the lim sup sense, because he didn't actually prove that the average existed. But
So when you say with rational two torsion, you mean full two torsion or just on element of?
I should have said, yeah, I mean full two torsion. So, right. And that makes the computation of the Selmer group easier. And then Johan de Jong in 2002, he proved that the average size, he averaged over all elliptic curves, but not over Q, but over a function field, the function field analog. And he proved an upper bound for the average size of the Selmer group. And then, yeah, okay. And the method here was, to count how many Selmer elements you have and how many elliptic curves you have up to height, and then take the ratio. So it's similar to what Mundrel did, except that it's not. He wasn't. It was less precise. So and he was only getting an upper bound, and the upper bound wasn't sharp either. So because it was, I guess, yeah. Okay. Anyway, so yeah, and then Bhargava and Shankar, they proved these beautiful results for Q, that they've computed the exact value of the average size of Selmer 2 and Selmer 3, and I guess Selmer 4 and Selmer 5 are coming. So I guess he as he's so I guess okay. All right. So So let me let me now switch to the blackboard and now to go to what the main topic of my talk is, which is to explain what's the underlying structure of Selmer groups that explains all these results. And why should the average size of Selmer be 3? And where does this funny distribution come from? I mean, it's not the first thing you would probably guess. Okay. Okay, so I'm going to start by talking about something that looks completely different. Okay, this is part 2. That was part 1. So this is going to be about random maximal isotropic subspaces. So I'm going to fix a finite field Fp, and I'll start with. I want to create a finite dimensional vector space with a quadratic form on it. And there's one easy way to do this, which is to start with a vector space without a quadratic form on it. So let's say an n-dimensional. Let's say an Fp vector space. So of dimension n. Well, what I'm going to do actually is take W direct sum with its dual. So that'll make it even dimensional. Is that what you? Oh, is P odd? Well, it doesn't really matter. Actually, I want to allow P to be even too, since I also want to be able to talk about. Eventually this is going to be connected with the P Selmer group, and I also want to talk about the 2 Selmer group. And so actually, some of the things I'm going to say are the difference being. Well, it'll be important that P is allowed to be 2. Okay, so. All right, so I take this and I take V to be W direct sum. It's Fp dual, so that's a 2n dimensional vector space. Yeah, and then I can put a quadratic form on this vector space. So in other words, it's a map here, and it takes a pair. So W comma. So W is an element of W, and phi is a linear functional on W, and just evaluates phi on W. And this is a quadratic form in the sense that if you take the associated symmetric bilinear form, then it's actually bilinear. So in other words, if you define this, so the usual way of going from a quadratic form to a symmetric bilinear form, then this is bilinear. So these x and y are elements of V. So they're these pairs. Okay? All right. So okay, and this is sort of the simplest kind of quadratic form you could have on a vector space. If you chose a basis for W and you chose the dual basis for W star, then this quadratic form would look like x1, y1 plus x2, y2 plus dot, 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 xn, yn. Okay, so and these things are called such a VQ. So this vector space with the quadratic form, this is called a hyperbolic quadratic space. Okay, now I want to talk about.
Forget about the W.
Yeah, I'm forgetting about the W now. Yeah.
There's one there is a W.
Yeah, that's right. I guess anything that's isomorphic to something that comes like this is called a hyperbolic quadratic space. And then I can give the notion of a maximal isotropic subspace. So isotropic means it's a subspace where the quadratic form restricts to be 0. So every vector has sort of length 0 in the. So it's a subspace. So I'm not defining subspace. Sorry. Okay, a subspace is maximal isotropic so first of all, I'll want it. Okay, so it should be equal to its orthogonal complement. And so that implies not only that it's orthogonal to everything in Z, but also that there's nothing. You can't make it any bigger. You can't throw in anything else and keep it orthogonal to everything itself. But that's not. That works fine when Q is odd. But when Q is even, there's an extra condition. So this is really just saying that it's isotropic as far as the symmetric bilinear form goes, but in characteristic 2, it's a little bit stronger if you also insist that the quadratic form restricts to 0. And so this will be the definition that I want. All right, so okay, so now what can you do with these?
So W is an example.
Yeah, in this example, if you construct V as here, yes, then W is an example. Yes, and so is W dual. That's right. And there are many others, at least if W is positive dimensional. Okay. Or maybe dimension greater than 1. Okay, anyway. So, all right, so now here's something you can do. So suppose I choose, so I have a V as above, and I choose 2 maximal isotropic subgroups. So I choose 2, say Z1 and a Z2. And I choose them at random. And when I say at random, I mean uniformly among all the possible choices. I mean, there's a finite dimensional vector space, so there are finitely many. I just choose them independently, uniformly at random. And then I look at the intersection. So the intersection of those 2 subspaces. So that's going to be another subspace. And I look at the event that the intersection has dimension D. And I ask, what's the probability that this happens? What's the probability that the intersection has dimension D? And it turns out, if you can do a calculation, and it turns out that as n goes to infinity, so n was half the dimension of V, this tends to the following expression. It's the product of, actually, well, let me go back here so you notice. Well, so hopefully you notice some. Okay, so there's that formula. And what does this one come out to be? You get a normalizing factor Sorry? Okay, so, and then the main factor, which is this, which is, and then P over. So basically, you just take all the 2's and change them to P's. All right. Okay, so now the question is this a coincidence? And of course, it would be a stupid talk if I said that there was. So the answer is going to be no, that's not a coincidence. Okay. Okay, but before answering this question about whether this is a coincidence, let me try to, instead of having to do this limiting process where I take n to infinity, I mean, wouldn't it be nice if I could just take, instead of having to take bigger and bigger vector space, suppose I could just take an infinite dimensional vector space and choose 2 maximal isotropics there and take their intersection. Now that doesn't, well, you have to do some work to make sense of that. For example, well, you'll want to have a vector space that's, well, you'll want the dual vector space to be the same, well, the same sort of, you want it to the double dual to be isomorphic to itself. So the natural thing to do is to equip this infinite dimensional vector space with a topology, and to make it in particular to make it a locally compact abelian group. So actually, I can generalize not just to FP vector spaces, but now let me just talk about all groups first for a second. And so there's a nice theory of Pontryagin duality for these. So you can define the Pontryagin dual, which is you take all the continuous homomorphisms from V to the circle group R mod Z, and then you give this itself the structure of some, you give this a topology, and it becomes another locally compact abelian group, and V double dual is isomorphic to V, and yeah, so this is the Pontryagin dual. All right, so, okay, now I want to put a quadratic form on this. So a quadratic form is just a map from, it's going to be, but now it's going to be taking values in R mod Z. It'll be a continuous map. And what makes it a quadratic form is, again, the condition that the associated, well, what should be the bilinear form is bilinear. So that this, so this is bilinear. Okay, and I'll make a couple of extra assumptions, namely, I'll assume that it's non-degenerate. So what would non-degenerate mean? So I'm going to assume that VQ is non-degenerate. So which means that, well, if you look at that symmetric bilinear pairing, that you can, if you fix one variable and view it as a function of the other one, you get a linear functional, so that the pairing induces a map from V to its dual. And so, namely, little v goes to the linear functional V as a function of this other argument. And then the condition is that this should be an isomorphism. Okay. And now I also want to have the generalization of maximal isotropic. And in this context, where well, if it's not a vector space, if it's just then the analogous definition, which people who study quadratic forms on finite abelian groups, the term that they use is called, it's weakly metabolic. So I just want to say that they use it because I mean, it's not a term that I invented. So, but anyway, I'm going to use it. So VQ is called this quadratic, this locally compact abelian group with quadratic form is called weakly metabolic. If it has I'll put some extra condition on it. A compact open maximal isotropic subgroup. And maximal isotropic is defined in the same way as before. So it should be something that's equal to its orthogonal complement, equal to its perp, and the quadratic form should restrict to 0 on it. Okay, so, and if you want an example of such a thing, you can do the same thing as here. Choose any locally compact abelian group W. Maybe it should be compact. Actually, if you want to make this compact, if you want to make this compact open. Yeah, so choose, let's do that. Choose a compact. Yeah, choose, okay. Yeah, okay, so actually let's make it a compact, like profinite group, profinite abelian group, and then take it with its direct, and take it. So if, for example, you could take a direct product of FPs, for example, and then take it with its dual and so on.
So then the dual is discrete.
Yeah, the dual would be discrete then.
So you could also have taken a discrete W.
Discrete, sorry? If I took W as being a discrete FP vector space, then my W dual would have been the compact open maximal isotropic subgroup.
So if you change compact into discrete in this definition, is it equivalent?
Well, I mean, let's okay. Let me give another example of how you can construct these things that's going to be relevant when I go back to talking about Selmer groups. So there's a construction. So that's essentially due. Okay. Well, it's closely related to a construction of Braconnier in 1948, where you can build these starting from a lot of little examples. So suppose I have a triple like this. And, well, I'll say that this is weakly metabolic, meaning that this is a locally compact abelian group, this is a quadratic form, and this is the compact open in the definition. So I'll just call the triple weakly metabolic. And suppose I have one of these. I have a whole sequence of these. So it's for all I in I. And I then take the restricted direct product of these V's with respect to the W's, with respect to these subspaces W. So what that means, an element of this means it's just like the direct product. It's a tuple, one where you have one coordinate from in each of these VIs, but the restricted direct product means that almost all but finally many should belong to the WI. Okay, so, and then you can define W to be just the direct product of the W sub I. And you can define on this, you can define on V, you can define a quadratic form just by summing these quadratic forms. So in other words, if you give me an element of this restricted direct product, define Q of V just by summing the quadratic forms on the components. And this makes sense because these V sub i's belong to W sub I for almost all I. So these are almost all the terms are 0. Okay, so then you can guess what the conclusion of this is. Then this triple is a new weakly metabolic, quadratic locally compact abelian group with a quadratic yeah. So locally compact abelian group with a quadratic form and subspace. Okay, so now I want to generalize this result I mentioned here, this proposition. I want to extend it to a situation where my subspace is allowed to be infinite, where my vector space is allowed to be infinite, and yeah, okay. So I'll need a couple mild conditions. So now I'm going to suppose that I have one of these, but I also want to assume that V actually is infinite, but it's not too big. It should be second countable, which means that the topology has a countable basis. But okay, anyway, it's just some technical condition. Don't worry too much about that. And I'll also want to assume that that V is actually an FP vector space, so it's killed by P. Okay, and then I can. So I will let then I sub V be. I'll define this to be the set of all maximal isotropic closed subgroups of V. I know there's at least one because it's weakly metabolic. The W is 1. And now, instead of intersecting two random maximal isotropic chosen uniformly at random from the finitely many, I'm going to say I'm going to choose things at random from this set and intersect those and see what the intersection dimension is.
So you're not requiring this compact, those two.
No, sorry?
Could be discrete.
Yeah, they could be discrete. And in fact, it will turn out, well, okay. So maybe I won't explain this in detail, but it's possible to put a probability measure on this set. Essentially by working with, well, there's a way of taking, if you take all the possible compact open isotropic subspaces in V, so let's call them X, and you can look at X perp mod X, then you get a finite example of this, and you can relate this to, this becomes a profinite limit of the corresponding sets for those sort of finite subquotients. And so by doing that, you can get a kind of, well, it's not quite a Haar measure since it's not a group, but it turns out to be a profinite, it's a profinite set where the transition maps in the profinite set are all finite to 1 with all the fibers being of the same size. And so you can define a uniform measure on this set.
So may I ask a question? Do I correctly understand that your isomorphism type of your V is completely determined by P? It's just a product of FPs accountably many, direct sum of the same number of FPs?
I'm not sure. Maybe that's right, actually. Okay, I'll think about that. But okay, so all right. So now let me take. Okay, so now let me state what's the analog of this proposition here. Well, it's basically the same. So if I now choose, so okay, this one maybe gets to be called a theorem. So actually, here I already have one maximal. I already have one element here. The W is one example. And actually, in this theorem up here, instead of having both of the subspaces move around, I could have just fixed one and let the other one be random. And you would have gotten the same distribution just because the automorphism group, the orthogonal group of this quadratic form, acts transitively. So it doesn't matter really what the first one is. It only matters what the relative positions of the two are. So here, I'm just going to use W as one of my subspaces, and then let the other one be random, and look at what the intersection gives. So if this is chosen at random, with respect to this probability measure, then the probability, well, okay, so I'll take the intersection of z with w and ask what's the probability that that equals d. A priori, this dimension might not even be finite, but it turns out that whereas w is compact open by definition, it turns out that z is discrete with probability 1. And therefore, the intersection is actually finite with probability 1, and there is some distribution over the dimension of this finite dimensional vector space. And it's exactly, well, I guess I didn't give it a name. Let's call this thing sort of CD, C of D comma P. And then you get that exact value. Okay. Okay, so this gives you another way of, well, this gives you a way of sort of maybe a more natural way of coming up with a distribution. Well, a more elementary way of finding that distribution that has nothing to do with arithmetic, nothing to do with Selmer groups or other thing. And maybe before I go on, so let me say a couple of things about other things about this distribution. I mean, eventually I want to relate this distribution to Selmer groups, but before I do that, let me just say a couple of properties of this. So there's another description of this same distribution that's maybe the easiest one of them all, but maybe it doesn't explain, well, maybe not quite as natural looking, but so there's an alternative description of this distribution on non-negative integers. So you choose a sequence of Bernoulli random variables, so B1, B0, B1, B2, etc. So, okay, so these are independent random variables. So and then the ith one is, well, it's a Bernoulli random variable, meaning this should be 0 or 1, and choose it to be 1 with probability 1 over p to the I plus 1. And now take all of those and add them up. So it probably converges. In fact, with probability 1, it converges. And so it converges 100% of the time, and it has the same distribution as the one I was just talking about. And so this makes it very easy, for example, to write down the generating function for this sequence of CDPs, if you want to do that. And you can also use it to compute things, other statistics of this distribution, like, well, once you have the generating function, you can compute all sorts of things. For example, so what are some of the things you can see? Well, maybe I'll postpone that later. I think what I want to do now is instead explain now how this connects with arithmetic, how it connects with number theory. So why am I doing all this stuff with quadratic spaces? So, all right, so let me first now talk about, eventually I want to talk about Selmer groups, which are global objects, but before doing that, I'll need some prerequisites regarding local fields. So here's a proposition. So I have an elliptic curve now, but now it's over a local field. Let's go over a completion of some of this number field k. Okay? And then I claim I can make one of these weakly metabolic things associated to this. And the vector space that I take is H1 of the p torsion of this elliptic curve. And maybe, okay, and the p torsion has a Weil pairing, which is an alternating form, taking values in the pth roots of unity. And if you take cohomology of this pairing, you get a cup product pairing that goes from V cross V into H2 of mu p. So there's a natural pairing. So the cup product of the Weil pairing, which goes to H2 of kV. And actually, I can let me actually put here, instead of mu p, let me put just the entire multiplicative group. So then it goes to H2 kV of GM, which is otherwise known as the Brauer group of kV. And for a local field, this is always contained in Q mod Z, and Q mod Z is contained in R mod Z. So I can view this as being well, this is the symmetric bilinear form. It's not a quadratic form, but it turns out that there is also a quadratic form that gives rise to this symmetric bilinear form. And maybe I won't describe where that comes from right now, but so it comes from, it has something to do with the Heisenberg extension, but I'm not going to, I think I'll leave that, you can leave that out for now. So it comes from a quadratic form, which I'll call little q sub v. This v, you mean this v? For most, well, it depends on, well, no, this is going to be a finite. This is going to be finite here. Yeah, I mean, if you were doing this over the only situation where this would be infinite is if you were working with a function field instead, and you're doing the p torsion and characteristic p using FPPF cohomology. In that case, this H1 would actually have a topology. It would actually be a locally compact FP vector space, and it would have this. That's one reason for using this general machinery. But in the case of a completion of a number field, this is just a finite. This is just a finite dimensional vector space. So okay. So that gives me a finite dimensional vector space with a quadratic form, and there's a quadratic form on it, and it's also weakly metabolic. I can show you a maximal isotropic subspace. Namely, inside that you have the image of the local points. So this thing, using the same descent sequence that I had at the very beginning, so I can. It's still here. Yeah, it's just this map here for one value of v. So this thing mapping into v, the image turns out to be maximal isotropic. And so the proof of this, well, it uses, to construct the quadratic form, you use Mumford's Heisenberg group construction. So, okay, I'm not going to explain this, but. And then to prove that this subgroup is maximal isotropic, it more or less boils down to the local duality theorems that were proved by Tate around 1960. All right, now I want to. So what's the analog for global fields of this? So now what do you do for a global field? So, well, I guess I'm really working with a number field, but. Okay, so now I have an elliptic curve over a global field. I can again define a V, and what I'll do is I'll use Braconnier's construction. You take the restricted direct product of all the local ones. So I take all the H1 KV EP. So those are the big subspaces, and I take the restricted direct product of those with respect to their compact, with respect to these maximal isotropic things. So these E of KV, mod P E of KV, and and then from this, by that construction, you get a quadratic form here, and you get a subspace. So this is a big. Now it's infinite dimensional. So this is, you get a big space here. And I can also write down a diagram like this. Well, it's really the same thing that's in here in the group there, the diagram that defines the Selmer group. So let's look at this mapping into. Well, I have the here I can. It turns out that that map beta, its image actually is contained in the restricted direct product. So I can put here this. Maybe I should have. Okay. Anyway, I'll just write V. So, and this is the same map beta. And over here, I have the product over all V of E of kV mod P E kV. And this maps in here, just includes in there by this map alpha. Okay, and now what is the Selmer group? So what does this have to do with Selmer group? So here's the main theorem. So the first part is that if you look at the image of those two maps in that diagram at the bottom right, the image of alpha and the image of beta, they are both maximal isotropic in that big space V. And then the second part is that beta is injective. And so, then the third part, which is really just a consequence of the first two parts, is that if you intersect these two maximal isotropic subspaces, well, what do you get? That's the same, because beta is injective, that's the same as taking the elements here that are in the image of this one. So this intersection is just the image of the P Selmer group. And beta is injective, so this is just isomorphic to the P Selmer group. So this construction exhibits the Selmer group as an intersection of two maximal isotropic subspaces in this infinite dimensional space. And so it gives you an explanation for why this Selmer, if you believe now that those things are random, that these subspaces in here just don't bear any relationship to each other, they're just sort of both stuck in there, then if you vary E, then these subspaces move around, and maybe the distribution over their intersection is the same as in that theorem. When I take two random subspaces in an infinite dimensional weakly metabolic quadratic space. So, okay. All right, so this gives you a prediction for what the distribution of not only the two Selmer group, but also for all the P Selmer groups, what they should all look like. So I don't know if I should say anything about the proofs of these theorems, but, I can say a little bit, I guess. For alpha, already by construction, the image of alpha was maximal isotropic, because it was defined by taking each of the local maximal isotropic and then multiplying them together. As for beta, the fact that one is maximal isotropic is deeper. It follows from, you use the reciprocity for the Brauer group, and you take the 9-term Poitou-Tate exact sequence, gives global duality, and you look right in the middle. And that gives you the fact that it's equal to its own perp. And for B, this turns out to be an easy consequence of Chebyshov density theorem and the fact that the CeLO P subgroup of GL2FP is cyclic. And finally, I said the last part just follows from A and B. Okay, so let me end then by saying what are some of the consequences of this. So now I'm going to take this as I'm going to take this as justification for a heuristic, namely that the Selmer group should be distributed like the intersection of two maximal isotropic subspaces in this infinite dimensional space, and see what does that predict. So I can now just read off some statistics about these distributions. So consequences. So what are the consequences of this heuristic? So, well, first of all, it should be. First of all, you should say. So the heuristic is that the probability that the dimension of Selmer group is D is exactly the formula, the CPD that I had on just like this one with the p's instead of the 2. And so you can ask, based on that statistics, you can ask, okay, what's the probability that the p Selmer group is odd? Well, this ought to be 1/2, right? Because it should be compatible with the root number, which is expected to be 1/2, 1/2. And you can actually see directly that this distribution gives equal weight to the odd integers and the even integers. And that comes from this alternative description of this as a sum of Bernoulli random variables. Because if you look at I'm not sure if I still have it here. I guess not. But if you looked at the first Bernoulli random variable in that infinite sum, the first one was 0 or 1 with probability 1/2 each. And it doesn't matter what you add to it after that, because it's going to be evenly distributed over odd with respect to odd and even after that. So this is 1/2. Well, that's not a very surprising heuristic. But also, if you take this probability distribution and you compute the expected size of the Selmer group, not expected dimension, but the expected size, so you get exactly what this gives you a possible explanation for the results that Bhargava and Shankar found, so that the expected size of the p Selmer group should be p + 1. And you can also work out from this some things that have not been proven in general, but that have been proved, I guess that were proved by Heath Brown for the 2 torsion in that family of twists. You can compute the moments of the size of the Selmer group. In other words, compute the expected size of Selmer group to the nth power. And this turns out to be p + 1 times p squared + 1 ... p to the m + 1.
Those e's on the left are expectations.
Oh, yeah, those e's are expectations. Maybe I should. Yeah, okay, sorry. I don't think anybody could have ever. Okay. All right. So, actually, one amusing thing I noticed last night, maybe some of you already. Suppose you take this distribution and you condition on the Selmer group being odd. So that means that. So it's going to be if the Selmer group is 1, 3, 5 or something. So that happens with half probability. But what do you think happens to the expected size of the Selmer group? I mean, you might think that would get bigger because now you're not allowing rank 0 anymore. You're not, instead of 0, 2, 4, 6, you're only allowing 1, 3, 8, 1, 3, 5. But it turns out, it's exactly the same. And what's even more miraculous is that if you do the same thing with the moments, the same thing happens. Even if you condition on the Selmer rank being odd or even, it doesn't change the moments. I mean, it almost contradicts the theorem that probability distributions are determined by their moments, but not quite, because this thing is growing so fast that it violates the hypothesis of those theorems. Anyway, this is a good example of 2 distributions that have the same moments.
So actually, that statement is easy to prove one of the coins.
Right, that's exactly right. You can get it from, it's very closely related to the proof that I gave for this. That's right. Okay, let me now say a little bit about what this implies as far as ranks of elliptic curves and Tate-Shafer-Average groups. What does this say? How does this relate to those things? So there are really 2 things I can say here. So first of all, this is something. So Carl Rubin pointed out to me. So if if you take this heuristic for the size of for the distribution of the Selmer ranks, but you do it not just for one p, but you have this heuristic and you know that it's valid for an infinite sequence of p's, then you can see what happens to this distribution as p goes to infinity. He mentioned this in his talk. And if you take this heuristic for an infinite sequence of p's, then this will imply, well, I mean, the numbers here, as that 2 becomes a p and tends to infinity, it becomes the distribution where it attaches a probability 1/2 to 0 and 1, and 0 to all the others in the limit. And so this implies that the average rank of elliptic curves, as you vary elliptic curves over a fixed number field, they should be at most 1/2. Because that's what the average Selmer rank is. Because this has to be bounded by the average Selmer rank. And if you also believe, then if you also believe the parity conjecture, well, it shouldn't be less than that. It's supposed to be 0 or 1 it's supposed to be even and odd with equal probability, so it can't be any less than that. So this would then predict what it seems that everyone believes these days, that the rank as it should be 0 or 1 with probability 1/2 each, asymptotically. Yeah, okay, and on the other hand, if you have the heuristic for just one p, so what can you get from that? Well, if you take that and you combine it with Delaunay's heuristic, who has an independent heuristic for the p torsion in Shaw, you can ask the question, what possible distribution on ranks, if you assume a prior distribution on ranks, and then Delaunay tells you what the heuristic for this should be given the rank, you can compute whether it's compatible with these Selmer group heuristics. And it turns out that, again, there's only one distribution on ranks that's compatible with both of these heuristics. And that's this one where it's rank 1/2, rank 0 or 1 with probably 1/2 each. So it looks like everything is consistent at least. So we don't know if these heuristics are true, but they look, well, at least there's some evidence are both theoretical and it's proved various statistics, the statistics of what Bhargava and Shankar have proved, it's consistent with that. Everything, it looks like it's a big, nice picture. So I will end here, and thank you for your attention.